So, now we start. So, it is 3D hydro only, but we will look at entropy. Okay. Now, it is a useful quantity, again not heavily emphasized. Vorticity is of course heavily emphasized, but not as much as it. I mean, so I would tell you few things which are new. Okay, you will not find anywhere else. So, entropy flux is new. Entropy spectrum is in fact trivial. So, what is entropy? I defined it before. Is omega squared. Omega is vorticity. So, omega squared. So, we will cover governing equations, mode to mode entropy transfer. So, you can generalize what happens for kinetic energy to entropy transfers, entropy fluxes, spectrum is trivial, which I will tell you, and then some numerical results. So, governing equation I will recap. This has been done in earlier lectures. So, in real space, vorticity is curl of u, okay, is a vector. We are working with 3D. We will come to 2D later, but vorticity in is like a vortex tube. So, this vortex and vortex tubes. Now, the equation for vorticity is curl of u cross omega. Okay. So, this is the form, and this is coming from curl of fu, and this is a viscous term. So, instead of nu grad square u, you get grad square omega. Okay. So, this has been derived if you look at your notes or look at the notes I gave you. So, you will find this. So, u dot grad u has become, and pressure has basically disappeared because of curl of pressure is 0, but u dot grad u has written is of this form. So, in Fourier space, so flux means you work with Fourier space, okay, that is best, though there is some derivation of flux in real space, but Fourier is most convenient. So, we will work with Fourier space. So, omega becomes I k cross u k, okay, and so omega. So, I take the old equation which I showed you in last slide, convert it to Fourier space. So, the nonlinear term becomes k, the u cross omega becomes convolution of the curl. So, it is not a product, dot product, it is a cross product. So, u q cross p and q is equal to k minus p. So, I sum over all p's, okay, and this is a viscous term. Now, this a cross b cross c can be written in terms of some vector identity. So, this a cross b cross c, well, this is a good thing to remember, a cross b cross c, what is that? B a dot c, the first one minus a dot 1 and 3, then c a dot b, okay. So, that is what I have done here. So, I k dot omega q u q and q dot u q u omega b. Now, this we derived it before, but it is just a recap, but you should pay attention. So, this is important, we need this. So, if you look at equation, so this is basically d omega by d. So, if I put a minus sign of this, it becomes plus and this plus, no. So, d omega, this is equal to d omega by dt, right, d omega dt minus n omega, forget the viscous term. So, the first term is q dot omega, yeah, so that your this p, yeah, this is a typo. So, qp. So, I have again made one mistake here. So, no, this is a mistake. So, this is vortex advection, this one. So, is carrying, so omega is carried by uq. So, this comes as u dot grad omega, right, this comes from this term u dot grad omega, right, because this will come from grad and this comes from u. Is that clear to everyone? So, in real space there are two terms, this u dot grad omega and this is the minus sign also, this is, I made a, so there is sign error as well, no, one of them come with a minus sign. So, this comes with a minus sign and this comes with a plus sign in the right hand side, okay. So, n omega, so let us let me just talk about n omega. So, I think there is an error of sign. So, which is plus sign? This plus sign, this is supposed to be this, and then the minus sign. So, minus becomes plus. Okay. So, this term is coming from u dot grad omega, and this coming from omega dot grad u. So, in real space, let me just write this, real space omega dot plus u dot grad omega equal to omega dot grad u plus nu grad square omega. This equation omega. So, this term is giving you this nonlinear term in Fourier space, and this one is giving you this nonlinear term. So, this term is advection. What is advection? So, this is basically total time derivative of omega, right? Everybody is done with fluid mechanics, no? So, this is material derivative. So, omega, if you sit on the particle, if you sit with omega, then when you go along with it, this is pushing this, the mean flow is pushing this vorticity. Is that clear to everyone? So, this term is advecting. So, this term is vortex advection, and this term is omega dot grad u is something stretching. So, this is vortex stretching. So, this one is vortex stretching. So, I did not look at it, but yeah, the terms are. So, k dot u omega u is vortex stretching. Okay. So, now let me ask the question, which one is going to increase omega overall? If I look at omega squared of the whole system, you can make a guess. So, advection will not increase, advection is just porting things. Okay, advection is just porting, it is just taking one same material one place to other place, it does not give you new material, but stretching can increase omega or decrease omega. Okay, it is expected to increase omega. Okay. So, vortex stretching is comes from the second term. So, there will be two kinds of energy transfers or entropy transfer, one is because of advection, other one is from stretching. Okay. Now, we can make this quantitative. So, equation for entropy. Now, that was for vorticity. Now, entropy I define as omega k mod square. So, omega k is a complex quantity. So, so this is modal entropy. Okay. Modal means for a given mode what is the entropy. Now, if I take the time derivative of this, so omega is function of time. So, mod omega square also will be a function of time. So, it will be just straightforward. Okay. So, this half will go away and this will go. It is very similar to what you do for velocity field. So, I will get now omega dot has two terms. So, entropy also will have two terms. So, this coming from advection Q dot EQ. So, this is advection and second one is stretching. Now, this is stretching and this is diffusion or dissipation you may call it. Now, in advection term omega is multiplied by omega, yes, and here u is multiplied by omega, a dot product. Okay. Multiplication is here is dot product. Okay. So, now we can do the same analysis like mode to mode transfer. So, this is energy. Now, let us develop this what happens for a single triad. Now, this for all triads. No? So, let us try to dig further and try to get some picture about how energy is flowing. By the way, so this one work I do not see many papers now, but if you look at book by Lumley and Tennekes and Lumley, there is a lot of discussion on mechanism of vortex stretching. So, flow should go like this and it should stretch, this is all in real space. Now, there is interesting discussion when you stretch it, frequency will increase just because of mechanics, no? If you stretch it, then angular momentum increases. Now, I would want personally to do it in another Fourier space, and I have not been able to. Well, I mean, I think if somebody wants a partner, we should try this one. So, understand in terms of transfers. So, I will exactly tell you what we should look for in terms of mode to mode transfer, and it can be done. So, we will look for mode to mode entropy transfer. So, same formula we for kinetic energy we can generalize this to entropy. So, instead of working for all possible triads in the flow, we focus on a single triad and its pair for complex conjugate. Reality condition requires that I should have also minus k, minus p minus q. So, we have a k prime p q, and this is k prime minus k prime, which is k minus p minus q. Okay. So, I have only one triad. So, for a single triad, instead of sum I will get few terms, the sum will reduces to only few terms, and so this is transport advection and this is stretching. Okay. So, the sum will involve 2 terms for stretching and 2 terms for advection, straightforward. No, I mean these are just long formulas, but if you understand physically, that is what they mean. So, this is omega omega multiplication k dot u. So, this is coming from u dot grad. So, this is advection term, omega omega is this advection. Okay. So, k dot u q omega p omega k prime and k prime u p u q omega k, and q is equal to k minus p, or q plus p plus k prime is 0. So, let us keep this notation. Okay. Vectors, okay, all vectors. Now, what about omega u? It just follows from the sum. So, sum has the u is replaced by omega and product is u with omega. So, u p omega k prime, I missed prime here, k prime u q omega k prime. Okay. This for a single triad, but kinetic energy has only one term, the first term, and these are all u's, everything was u. Now, with vorticity, of course, there will be more complication. So, now we have vorticity to vorticity and velocity to vorticity. So, these are the terms, and this should be telling you is a stretching term. So, we should analyze this for stretching. When you stretch it, how does the vorticity change? So, mode to mode, and from the DNS we should pick the data and really see whether it is stretching. Okay, let me just do few more steps and close my derivation. This is entropy increase, rate of change of entropy at a wave number k prime by 2 terms. So, and 2 wave numbers. So, it's k prime, there is increase in k prime from both p and q. So, it should be called what? Combined entropy transfer. Okay. So, this is a combined, actually sorry, this should be combined entropy transfer. Okay. So, combined entropy transfer to k prime from p and q. Okay. And now this satisfies some properties. Now, as I said, you can do it. The first one you have to write for s omega omega p k prime comma q, and same thing for with q. Sum them up. Incompressibility condition has to be used, and if you use that, then you get this is 0. But intuitively it is obvious, because this is not stretching, it is just advection. So, you are just porting from one place to other place. You just sweep your floor, but you just transferring the dust from one place to other place. It does not really change the dust unless you take it out. Okay. So, this is just advection and does not change the entropy, the first term, but this one can change. In fact, you can just do the sum, you cannot show that it is 0. So, if I have again 3 terms from p and q, just add them up, this is not equal to 0. The sum is not equal to 0. Okay. So, that is the result for combined entropy transfer. But now, can we think of mode to mode transfer? Now, same question, this is these two terms together form, give the rate for P to K prime and Q to K prime is total. But can I say individually how much goes from P to K prime and how much goes from Q to K prime? It turns out there is a proof which I will not prove it right now, but is there in the book. This term is very similar to what we do for kinetic. This is P to K prime. Whatever is product of omega with omega is a giver and receiver. So, this is a giver and this is a receiver. So, K prime is a receiver, right? K prime is definitely receiver. So, I identified whatever is dot product omega K prime with is a giver. For this term, this is a receiver, this is a giver. Okay, is that clear? And here what is this omega uq? Is a mediator, because it is multiplying with K prime, which is u dot grad, this term K with u. So, this is a mediator, it is a advector. Something advecting is only driving the thing, is taking things one place to other place. It does not participate in the transfer. So, this is omega to omega transfer, right. So, giver is omega, receiver is omega, so omega to omega transfer. So, this is basically omega omega K prime P Q, and this one is omega omega K prime Q P, because here Q is giving and K prime is receiving. Now, same idea here, U is giving and K prime omega is receiving. So, this is a giver and this is a receiver, and this is a mediator. Okay. So, this is S omega u to omega, right. So, the notation is the second argument is a giver, the second argument here in the superscript, u is a giver, omega is a receiver, K prime is a receiver, P is a giver and Q is a mediator. Okay. And what about this one? Yes, OS omega u K prime Q P, because Q is a giver, UQ is giver and omega K is a receiver. Here this is like giver is somebody else, is not, omega is getting from U field, is stretching. So, it is not among themselves, but it is some other party. So, this is what it is. Okay. So, the proof I will not do it here, it is quite long, but it is very similar to what you do for kinetic energy. For completeness I read in the book, but it is just intuitively this is what it is. So, let us see this result. So, without proof I am just stating that this is omega p to omega k prime with uq is a mediator, giver, receiver, mediator, and the picture is, it comes from u is advecting, mediator, this is giver and this is receiver, and the picture which is so is coming from here, omega p to omega k prime with omega uq is a mediator. So, this is mediating, wavy is mediating. Okay. Now, the for other one omega u. So, here up is a giver and omega k prime is a receiver. Okay. So, this is here, and it comes from omega, this is a mediator, giver, receiver, and this is vortex stretching, and up is, so the arrow is not very, up is a giver, this is a receiver and this is a mediator. Okay. So, this is mode to mode, u to omega, we just discussed mode to mode transfer. So, there is vorticity to vorticity and there is a velocity to vorticity. Now, we can define flux with that, So, nonlinear term, so that was in a triad, but you have many triads. So, that will define energy going from one wave number sphere inside to outside. So, it is just like Kolmogorov flux, very similar. So, this was omega to omega advection and this is u to omega. Now, I do it for many triads. So, I derive for single triad mode to mode, but just do it for many triads. So, this will give you, so u omega is basically sum over all p's, right. So, this coming to k from p. Now, as I said, if I sum over all k's, I sum over all k's d by dt of this. So, there is sum over k, sum over p, sum over k, sum over p. This is 0, because advection is basically conserving instead of phi, and this sum is not equal to 0. Okay, this is instead of phi coming from velocity field by stretching. Okay, so in fact, this is not only for all, but it is true for any region, but giver and receiver in the same region. No? You sum over, so omega omega is 0. This you can show for like from the conservation law which I told in the last set of slides, and this is not equal to 0. Okay. Now, from this, so again you can do more formal thing which I did in the for vorticity, but velocity field, but I will skip all that. You can define flux, and definition is once you have the transfer from one region to other one mode to other mode, then you can define flux. That is as formal as any. I mean, you no need to motivate further. So, these are now the picture is more very looks slightly complex, but if you look at the picture slightly more carefully, then you will find the idea. So, these are velocity sphere. Okay, the brown is velocity sphere. The mode inside is u less, mode outside is u greater, and we also define vorticity sphere. So, omega less is the modes within the sphere, omega greater is modes outside the sphere. Okay, is that clear? Though omega and u are related, but we define two different spheres. Now, u sphere, u less sphere can give, now this is Kolmogorov flux, right, modes inside giving more energy to modes outside, and this was written as pi u, in fact it can written as like this, we did in the last lecture. Radius of the sphere is k naught, it is sum, p is giver, so it is less than k naught, and the receiver is outside, so k greater than k naught, s u u k prime k p q, k prime is minus k, k prime is minus k. So, you can write, is that correct? So, this we define. Now, we can also define flux for instead of phi. So, let us look at the simple one first, this one. So, what is this? Omega less to omega greater. Who is the receiver and who is the giver? Omega greater is a receiver. So, below is the receiver. Omega less is the giver. So, giver modes must be within the sphere and receiver must be outside the sphere. So, I just define it here. So, let us erase this one. So, omega less to omega greater is defined as receivers. So, omega omega to omega transfer, which I defined mode to mode. Giver is p, receiver is k prime. So, this is receiver giver. So, giver must be within the sphere and receiver must be outside the sphere. You just sum it up. So, this is omega to omega. In fact, there is within omega there is one, this is like Kolmogorov type, very similar, but it is omega to omega, and this is advection, vorticity advection. Now, omega gets from u by many channels. How many channels? You got 1, 2, 3 channels. Okay, this is important point. U cannot give to u itself within the sphere, but now omega within can get from u within. So, this line is u less to omega less. It can be non-zero, and so we have u to omega, but both receiver and giver are in the sphere, but giver is in this sphere and receiver is in this sphere. Oh, sorry. So this other one. Okay, let me focus on this one first. This one, both are within. Okay, so this is u less to omega less. Now we have u less to omega greater. So, here to here this is one. So, this is P is giver is less, but receiver is more. So, this vortex stretching, plus there is one more which I did not write it here, this one, giver and receiver both are outside. Now, this what needs to be computed in simulations, and this work is incomplete. In fact, nobody has done this computation as far as I know. I mean, no, in fact, mode to mode omega transfer nobody has given the formalism. So, we are the people who construct all this formalism. So, we can also define variable I am sorry Stuffy flux. So, is very similar on the similar lines for variable energy flux, but like if I look at entropy of a shell, it can change by fluxes, but there are now 3 fluxes. There is not, there is one flux is within itself. This was we had, the first one was we had for kinetic energy, right, flux here minus flux there, but now these are the flux coming from outside. So, this derivation I am not doing it here, but I derive in my notes. So, variable entropy flux will involve 3 fluxes, but I will not, so I will not detail this. So, this one is coming from external force, and this is a dissipation, and this one. So, if this is 0 under steady state, then we should get, and even in inertial range, then this must be constant, but I am not sure whether this is steady. This also should be studied, whether energy entropy keeps increasing or it saturates. I would like to see in simulation. Okay. Now, this is I am just flashing it as a something to test in simulations. Okay. So, we can also define shell to shell transfers. Now, there are 2 of them, omega omega and u to omega. So, remember the shell, this is the giver shell and receiver shell. So, P belongs to M giver and K prime belongs to receiver shell. So, this is shell to shell. So, is M to N, omega to omega. You can also define U to omega, M to N. So, there are 2 channels of transfer, omega to omega and U to omega, and they give you a shell to shell entropy transfer. Okay. So, what is entropy spectrum? That is by dimensions, not dimension, because omega is curl of u. So, k cross u. So, omega k is mod of this is k u k, correct. So, spectrum of u omega is u k cross k squared. So, spectrum is straightforward, just Kolmogorov theory, but the velocity field follows Kolmogorov theory. This is a funny situation. My velocity field is Kolmogorov, but entropy is giving somewhat new, well, I mean it has not been studied, that is why I meant entropy has not been studied so carefully in Fourier space. So, spectrum is, this is 100% sure, because it just follows from Kolmogorov theory, but the fluxes are what we need to compute. So, spectrum is fine. So, numerical simulation. So, this was done by Subhadeep, who is in our lab, a student. So, he computed this flux has been there in Tarang. So, somebody has to just run it. So, these are fluxes from omega less to omega greater, that omega channel is k squared and u less to omega channel, only one channel has been studied, and this is omega to omega and this is u to omega, and they are not constant. Okay. Now, my question is, so there, so it does, what about the time derivative of this? Is it when this omega is growing or becomes steady in the under steady state? I believe it should become steady, but one should check. And what happens to this in the inertial range? And also the picture of stretching in Fourier space, how does it look? So, which mode? So, we can make a triad, but we can construct triads. No examples which I have constructed in the class. You try to do it, not well. Many of them do not give stretching. In fact, they give you decrease in omega. So, this is important point, let me make this point clear. If I construct any arbitrary example for sine cos, cos sine, which we have been playing around, compute the stretching, or just see whether omega will increase or not, mode to mode transfer. It turns out omega may decrease. In fact, I find many times omega decreases. It tells us one important point. It tells us that it is the organized structure of the steady state that will give you stretching. Any arbitrary field configuration will not give you stretching. So, stretching, increase of entropy, which is said that it stretches it, is for flows which are already reached steady state or is evolved state. Not all, any configuration of velocity does not give stretching. Is that clear to all of you? So, we need to look at the simulation data, construct triads, and then look at stretching. In fact, we need to analyze the data of the developed flow. So, the fluxes are, so if I take any arbitrary flow field, compute Kolmogorov flux, what will I get? Not from the simulation, just generate any velocity field. You will get, you basically get 0 flux, random. But is evolved field, its phases are in such a way that it has organized itself, that gives you constant flux. So, organization comes by evolution. This equation is leading towards that organized flow. Okay. So, this stretching is what we should look at from the developed data. So, these are some things one needs to work out. Okay. So, I think we stop. Thank you.